Every day, invisible forces are doing mechanical work for you. When a ceiling fan spins above your head, when a refrigerator hums through the night, when a phone vibrates, a washing machine turns, or an electric car accelerates forward, none of these machines are powered by fire, muscle, or steam. They are powered by fields, magnetic fields, electric fields, and a set of physical laws discovered step by step over nearly 2 centuries. This is the hidden physics behind everyday machines. Welcome to Mattermosaic, piecing together the universe, one discovery at a time. In this episode, we trace the real historical and physical origins of electric motors and fans, from early 19th century laboratory experiments in Europe to the standardized machines that now drive modern civilization. This is not a story of sudden invention. It is a story of gradual understanding, shaped by copper wire, rotating magnets, and equations that transformed invisible forces into mechanical motion. At the start of the 19th century, machines depended on direct physical forces. Water wheels powered mills along rivers in England and France. Windmills turned grain across Persia, the Netherlands, and Spain. Steam engines driven by coal powered factories in Britain after James Watt's improvements in the 1770s. Electricity at that time was not a source of power. It was a laboratory curiosity. In 1785, French physicist Charles-Augustin de Coulomb quantified electric force using a torsion balance in Paris, establishing that electric charges obey precise mathematical laws. But electricity still produced sparks, not motion. The missing link was magnetism. The breakthrough came in 1820 in Copenhagen, Denmark. Hans Christian Ørsted, a professor at the University of Copenhagen, observed that when an electric current passed through a wire, a nearby compass needle deflected. The effect was reproducible. Electric current generated a magnetic field. Ørsted published his findings in July 1820, triggering rapid investigation across Europe. In Paris, André-Marie Ampère formulated mathematical laws describing how electric currents create magnetic forces, showing that magnetism could be explained entirely by moving charges. In Germany, Johann Schweigger developed the galvanometer in 1820, allowing weak currents to be measured reliably. Electricity and magnetism were no longer separate phenomena. The first true electric motor emerged in London in 1821. Michael Faraday, working at the Royal Institution, demonstrated electromagnetic rotation. A wire carrying current rotated continuously around a magnet immersed in mercury, sustaining motion as long as current flowed. This was the first verified conversion of electrical energy into continuous mechanical motion. Faraday did not commercialize the device, but he established the physical principle behind every electric motor that followed. In Budapest, Ányos Jedlik independently developed a small electromagnetic rotary apparatus in 1827 and described an early form of the dynamo principle, though his work remained limited in circulation. In 1834, Thomas Davenport, a blacksmith from Vermont in the United States, built the first patentable electric motor and demonstrated it driving a small printing press. The motor worked, but it was inefficient and expensive. The limitation was power generation, not physics. That obstacle was removed in 1831. At the Royal Institution in London, Faraday discovered electromagnetic induction, showing that a changing magnetic field induces an electric current in a nearby conductor. This relationship, known as Faraday's law of induction, described the reverse process of the motor. Mechanical motion could produce electricity. This discovery laid the foundation for generators and electrical power grids. During the 1860s, engineers such as Werner von Siemens in Germany and Zeno Begrama in Belgium built practical generators capable of delivering sustained electrical current. By the 1870s, power stations began operating across Europe and North America, allowing motors to run continuously. Early motors relied on direct current and used brushes and commutators that sparked, wore down, and limited efficiency. A major transformation occurred in the 1880s with alternating current systems. Nikola Tesla, working in the United States after arriving in 1884, developed the concept of the rotating magnetic field. In 1887 and 1888, Tesla patented polyphase alternating current motors that eliminated brushes, producing rotation through phase-shifted currents that created a continuously rotating magnetic field. At nearly the same time, Galileo Ferraris in Turin, Italy, independently demonstrated rotating magnetic fields in 1885. The underlying physics was already unified. In 1865, James Clerk Maxwell published equations showing that electric and magnetic fields are components of a single electromagnetic framework. Motors were no longer experimental devices. They were applications of established law. By the 1890s, alternating current motors powered factories, elevators, and transit systems. Electric fans followed soon after. In the United States, engineers such as Schuyler Skates Wheeler developed practical electric fans during the late 19th century. By 1908, General Electric introduced consumer electric fans for residential use. Inside these machines, the physics remained unchanged. Electric current flows through copper coils, creating magnetic fields that exert forces on a rotor, producing torque and rotation. In induction motors, rotor currents are generated by the rotating field itself, a direct consequence of Faraday's law. These mechanisms are mathematically described, experimentally verified, and validated by continuous operation worldwide. By the mid-20th century, electric motors consumed more than half of global electricity production. Research shifted toward efficiency, materials, and control. In 1957, variable frequency drives were introduced, allowing motor speed to be controlled by adjusting current frequency. Later developments in Japan, Europe, and the United States led to brushless DC motors that replace mechanical switching with electronic control. Despite their name, these motors still rely on alternating magnetic fields. Ceiling fans, computer cooling systems, washing machines, electric vehicles, and industrial robots all operate on principles established between 1820 and 1888. No new fundamental physics is involved. What makes electric motors remarkable is not their complexity, but their invisibility. No flame burns, no piston strikes, no visible force pushes matter forward. Instead, fields perform work. Magnetic fields store energy. Electric fields drive charge. Arranged precisely, they produce motion. Every fan spinning above you is a physical record of cumulative human knowledge, from Ørsted's compass in Copenhagen, to Faraday's rotating wire in London, to Tesla's rotating fields in New York. Each contribution was experimental, published, and verified. No single individual created electric motion alone. It emerged from collaboration across nations and decades. Every time a motor turns, it is not just a machine at work. It is 2 centuries of physics, quietly rotating in copper and steel. This is Mattermosaic, piecing together the universe, one discovery at a time. If this episode expanded how you see the machines around you, like this video, share it with someone who enjoys understanding how the world works, and subscribe to Mattermosaic for more grounded science stories. Always remember, every everyday object hides a deeper story of discovery, and the next one is waiting for you in our next episode.